Good afternoon. I am extremely honored and privileged to introduce our chief guest of third section, Dr. G. Sahaya Tennis Babu Sir, Assistant Professor, Department of Physics, Chettinad College of Engineering and Technology, Karur. Sir graduated with MSc Physics and MPhil from St. Joseph College of Bharatidasan University, Trichy, and completed doctoral degree from Anna University. And Sir acting as visiting research scholar in Indian Institute of Science, Bangalore, and also served as visiting research studentship in University of Malaya, Malaysia. Sir's area of interest are micro, meso, nanostructured materials, organic, inorganic, hybrid, metal halide perovskites and chalcogenide nanoparticles, optoelectronic, piezoelectronic, and nanopyroelectronic, thermoelectronic generator applications. Sir has published more than 9 international articles in well-reputed journals and presented an impressive number of conferences. Sir also delivered many invited talks in national and international conferences. With Sir's best research experience and academic excellence, I am happily inviting Dr. G. Sahaya Tennis Babu Sir to deliver his speech entitled on perovskite nanomaterials for next generations. The section is over to you, sir.
Yeah, thank you very much, ma'am. Am I audible clearly?
Yes, sir, you are audible.
Yeah, yes, my PPT is visible. Perfect.
Yes, sir. But it is not in
slideshow
mode, sir.
Yeah, what about now, ma'am?
Yes, sir. Yes, sir. It's visible. Thank you, sir.
Yeah. Okay, fine. Shall I proceed?
Yes, sir.
Yeah. Very good afternoon, everyone. Myself, Dr. G. Sahaya Tennis Babu, working as an assistant professor of physics at Chettinad College of Engineering and Technology, Karur. First of all, I would like to thank the organizing committee members, especially Dr. Pongudi ma'am, for giving me this opportunity to present my research work in this faculty development program, which is sponsored by AICTE ATAL Academy on novel materials for next generations. So today I'm going to give a talk on perovskite nanomaterials for emerging applications. So these are my outline of my talk. So first I will give a brief introduction about nanotechnology and nanomaterials, functional materials and optoelectronic devices. And I will give a brief overview on perovskite nanomaterials, especially on the metal halide perovskite nanomaterials and their importances and features. And especially I would like to focus on perovskite nanomaterial synthesis through adapting different approaches and their applications on optoelectronic devices. It includes solar cells, light emitting diodes, laser, photodetector, and radiation scintillators. Finally, I will conclude my presentation with the current status on perovskite optoelectronic devices and challenges and their opportunities. So this is my short outline. So I will be briefly dealing about perovskite nanomaterials in all dimensions, from 0-dimensional to 3-dimensional structures, and their fabrications for the application of solar cells, LED detector, and laser. So in general, materials are used widely in olden days and nowadays also. So in olden days, before the 3000 years ago, people have started to use many woods, bones, and some kind of wax, stars in the age of Stone Age. And after that, they have invented some kind of metals, elements in the earth, and they have used some copper, tin, which is called as a bronze materials in their daily lives. And after that, they have invented iron to make steel, glass, and some kind of minerals to fabricate their ornaments and their war equipments, everything. In the Middle Age, people have started to find out many polymeric based materials, especially on ceramics and porcelain based materials. So those kind of glasses and some kind of a composite material which is composed of metals and ceramics, people have started to use in the year of 1300. And after that, people have used many multi-variety of composites and steel and many other element material which are all available in the periodic table. So nowadays we are living in the era of information age. So now we are using most of the devices with made up of silicon-based material and multiple composites of polymers and nanostructure materials, especially on metamaterials. So these are the outline of a material development by each and every era. So this is a short outline. So in the Stone Age, people have used stone for their daily lives, and they have used bronze, and they have used iron also. And people, when they have identified silicon in the earth, they have started to utilize on many devices. With the help of that, we have got many modern advanced technological devices with the help of silicon-based materials. So from the year 1962 till that, we have received many numerous number of modern devices which made up of silicon-based materials. So coming back to the nanosensor technology, you are all aware of that. The technology which deals in the power of 10 power minus 9, that is called the nanosensor technology. So this nanosensor technology which deals about preparation of the material which is in the nano range. It may be nanostructure materials in the form of particles, composites, supramolecular assemblies, and multidimensional materials, including 0 to 3-dimensional materials. So after we have fabricated this structure, we have to evaluate their structure and their properties and their possible applications with the help of some kind of nano tools, which helps to characterize them. So there are various fabrication techniques, instrumentation techniques, and
excuse me, sir.
Yes, ma'am.
The PPT, the slides are not changing, sir.
Okay, so let me use like this. Is it fine, ma'am?
No, sir. Yes, now it's moving.
Yeah, okay. So sorry for the inconvenience. And
continue, sir.
yeah, fine. Yeah. So people have used to characterize this nanostructure material with the help of many nano tools using many instrumentations and computational techniques to predict their properties and their possible application in future devices. So with the help of these nanostructure materials and tools to characterize them, people have identified in many various fields to fabricate nano devices with the help of molecular electronics, micro electrical mechanical system, biomems, and lab-on-chip technology, and device miniaturization, and as well as for the sensors and directions. So these are the outline of the nanosensor technology, which plays a vital role in our daily life. So this image shows the application of nanomaterials and their sciences in all other fields, including energy conversion and storage fields. Here I have mentioned the application of the nanomaterials in hydrogen generation, carbon dioxide capture, sensors, thin film, solar energy, geothermal energy, biomass, water, and nuclear and electricity production. So when we deal about each and every field, each and every area of energy conversion and storage, the importance of the nanomaterials is a wide important one. And if we consider about solar cell materials, okay, so that material help you to understand the application of different materials, starting from the silicon to nowadays the emerging perovskite materials also applied for the solar energy. And the storage, corrosion, biocatalysis are listed here. So we will be discussing about the thin film fabrication, light emitting sensors, thermoelectricity in our upcoming slides. So especially I would like to focus on electronic materials. We already know that there are three kind of electric material available: insulator, semiconductor, and conductor. When the conduction band and valence band are getting overlapped with each other, that material are called conductor material, which has less energy gap value. And when the conduction band and the valence band of the material, which is arranged in a kind of a separately kind of a wide region, kind of a large energy band gap between those two bands, those material are called insulator material. In some cases, in between these two conductor and the insulator materials, there are some novel materials are identified. Those materials are called semiconductor. They are arranged in particular specific energy gap distance between conduction band and valence band. So these are the material that we are going to discuss today: semiconductor nanomaterials, which are used in the optoelectronic devices. Yeah, semiconductor nanocrystals. So nowadays, people have started to apply these semiconductor-based nanocrystals for the application of display applications. As shown in the figure, the new Samsung ultra high definition TV has been coming to the market with the help of fabricated by indium phosphide nanocrystals as an emitter in this wide display technology. So in the upcoming future, in another 5 to 10 years, many LED and quantum dots based devices also coming on the row for the benefit of the future kind. And when dealing about the nanoscience and technology, this important parameter plays an important role, quantum confinement. So when we deal about that, when we change the size of the nanomaterial from kind of a higher size to lower range, the band gap also getting increased. So that's the reason for the quantum confinement effect. And as well as the color of the materials also getting changed. When it is at a big size, it will be looking like kind of a red color in the case of a quantum dots. This is called an example of a cadmium sulfate quantum dots. When we change the size of the materials and their crystal size are getting reduced to 2 nanometer and their band gap is also getting increased. And it is noted to understand that the color also getting changed from red color to blue color. So this is happening due to the dimensional change of the materials from the 0 dimensional to 3 dimensional, and as well as their density of energy states are getting changed for the structure to structures. When it is called quantum dot, wire, well, and bulk semiconductor, the density of changes are getting like a peak size and narrow size and stepwise like region. In addition to these kind of quantum devices, many other colloidal materials are also available like nanosheets, nanowires, and quantum dots. So this lecture is mainly based upon semiconductor nanocrystals. So this is the general outline and general basic of the how to fabricate a colloidal semiconductor nanocrystals at a high temperature region. We have to choose some precursor material to form some kind of a precursor kind of a formation, and after that they will be allowing to form a nucleation. So the nucleation will be formed in the temperature between 100 to 300 degrees centigrade up the maximum, and it will leads to form the nanocrystal. And after some kind of a washing and purification techniques, we can easily get into the nanocrystal solutions which are all kept in some kind of a solvents. So these are some kind of a fundamental uh, technologies to fabricate colloidal semiconductor nanocrystals. So coming back to the functional nanomaterials. So functional nanomaterials are nothing but a compound that is well controlled and organized by the molecular body, which is available in the nanometer level scale. So a nanomaterial can be prepared to use them to apply them for a specific function. It may be fluorescence, strength.
Excuse me, sir.
Yes, ma'am.
There is some noise and very low volume, sir. I think you can adjust the mic or.
Okay. What about now, ma'am?
Okay, sir. Now it's okay.
So regarding the functional nanomaterials, the functional nanomaterials have been applied in many fields, including medical, sensor and monitors, and the electronic field and energy field. So I am going to discuss about the application of functional nanomaterials in the energy field, especially on solar cells and other optoelectronic devices. So optoelectronic devices are nothing but it's a device which is made up of the combination of two field, optics and electronics. So the optoelectronic device, which is easily defined as conversion of optical energy into electrical energy and vice versa. So the optoelectronic devices coming classified into three major categories: sensors, couplers, and emitters. So in the emitter category, light emitting diodes, lasers are fall into the category. In the couplers, people have shortly started in the use of LED sensors and fiber optic devices. So we can have three plus and emissive. So this made optoelectronic device. So I will be discussing about solar cells. So solar cell is nothing but an electrical device that converts the energy of sunlight which falls onto it into electricity with it is produced with the help of photovoltaic effect. So these are the typical architecture of a schematic of a solar cells, which has n-type, p-type semiconductor material and front contact and rear contact, and above that people have coated anti-reflection coating. So with this help they have produced electricity from this cell. And the structure of the solar cells is mainly classified into three main parts. First one is called absorber, and second one is called collectors, and third one is called metal contacts. So the main role of the light absorber is to converting the incident sunlight photons into holes and electrons. It is the main role is to separate those two carriers, and the charge carrier collector's role is to capture those carriers from the top end and bottom end. And the metal contact's role is to transfer the carriers to the circuit to release the to receive the electricity from the particular device. So this is the schematic of a solar cell. That is the Walden device structure. N-type semiconductor and p-type semiconductor are used as a light absorber and a light emitter purpose. So this solar cell have been invented in the year 1954 in the Bell laboratory, and they have received very low number of power conversion efficiency. With the help of modern advancements and technologies, in the 2014, people have modified it, and they have stacked their structures to kind of a well stacked one, and they have achieved almost 35% efficiency from the silicon based solar cells. So after the application of the silicon, people have started to look out the alternative to silicon, because silicon is high cost and their fabrication cost is also very high. So for that, people after the year of 1970, they have started to look out various other alternative material to silicon based materials. So people have started used to amorphous silicon and thin film based materials like cadmium, copper, indium, gallium sulfide. And after that, in the year 1990, people have started to use third generation photovoltaic materials, dye sensitized solar cells, organic photovoltaics, and quantum dot sensitized solar cells, and after that, perovskite solar cells. So these perovskite solar cells are falling to the category of third generation materials. So in this kind of a second generation and third generation, people have used various number of nanomaterials and nanostructures for the application of solar cells. They have used particles, rods, wires, and tetraboards also to use them as a charge carrier and charge collector role. So these are the tilted materials which is used in the solar cell applications. So in the above figure, it is noted that I have mentioned the three category: perovskite, silicon, and copper, indium, gallium sulfide. So this red color shows the absorbance range of the perovskite based material. So the perovskite can be able to receive the photon energy, which is having the energy value from 1.5 to and above. And as well as silicon can able to receive the sunlight energy from the electron voltage from 1.0. So that's why the reason silicon is on the top, and it is expected that the perovskite also can beat the absorption efficiency of the silicon very soon. So that's the proposed one. With respect to the Shockley quasar limit, they have predicted that these three materials, crystalline silicon, gallium arsenide, and perovskite, and gallium indium phosphate, which are all considered as a prospective material to reach the maximum power conversion efficiency from these kind of solar cell devices. So once again, the schematic of a solar cell with respect to the various generation, the age diagram depicts the schematic of a traditional silicon-based solar cells. In the structure, people have used p-type, n-type junction, which is made up of by silicon-based devices. And above that, they have coated some anti-reflector coating and some metal contacts to receive the charge carriers from the device. And they have just little modified with the silicon with other p-type and n-type material like copper, indium, gallium sulfide, cadmium sulfide material. And they have used zinc oxide as a low resistance and high resistance layer to receive the charge carriers from the particular device. In the third generation, people have used a dye sensitized solar cell in order to reduce the fabrication cost of first generation and second generation materials. And in the fourth generation, people have started to use, instead of the dye, they have used perovskite materials, which is called hybrid based perovskite. So that kind of a perovskite material only I am going to discuss today. So this is the classification of the various thin film based materials so far utilized in the photovoltaic purpose. So compare than the other traditional cadmium telluride and gallium arsenide based systems, the methyl ammonium bromide and methyl ammonium iodide, which are all called hybrid perovskite material, which are all having absorption coefficient in the range of 10 power 5 to 6. It is predicted that they can also be used for the industrial level fabrication of solar cell devices for the future photovoltaic applications. So it is predicted that this material also having environmental impact compared than the other traditional materials, silicon, amorphous silicon, cadmium telluride, and copper indium sulfate based materials. So why the impression is only towards on the perovskites? So the beauty of the perovskite is it relies on the structure, property, and processing. So all these three parameter which accepts and it reveals in the results in the form of performance of the particular device. So the mainly the structure of the perovskite is called ABX3. A is kind of a plus one side cation, B is called 2 plus side cation, and X must be a halide atom. So in general, people have used various A side cation, B side cation, and X side halide atoms. And sometimes people have started also looking out some other two-dimensional perovskite system that's just replacing their A site with two-dimensional organic cations, phenylethyl ammonium, butyl ammonium, ethylene diammonium, like this material. So by this way, they can be able to fabricate the perovskite structures. And after that, they have started to analyze their property, especially on the optoelectronic aspect, to find out the optical band gap value, whether it is fall in the category of 1.2 to 3 electron volt, then only it can be useful for the PV applications. And it is found that when we change the A site and B site and halide atoms, it is understand that their band gap energy also getting able to tune. So the tunable band gap property is an important one in these perovskite parameters. And the most important one is the processing of the perovskite films. We can easily fabricate this perovskite inside the glow box and outside the glow box also. So we can easily fabricate at the ordinary room temperature. In some perovskite also not able to form perfectly. In most of the other kind of a perovskite material is easily able to fabricate and process in the room temperature. So if we optimize these three parameters, structure, property, and processing, it is expected that this perovskite material will be able to perform very good with low potential loss, high and narrow emission, and it must be large photodetectivity. So it is expected that this perovskite material can be able to produce the open circuit voltage from 1.14 volt and the short circuit value from 24.92 and the fill factor 79, and it is theoretically predicted that they will be able to produce 22.7% power conversion efficiency. So this perovskite solar cell research has started in the year of 2009 with the help of Tom Miyasaka from a Japanese professor, and after that his postdoc student Professor Henry Smythe from University of Oxford has started and working on this perovskite material till date. They have he is the person who has done most of the prominent and notable work on these perovskite materials and devices, and this is the called National Renewable Energy Laboratory, which is located at states. Every year they are releasing a solar cell efficiency chart. From this chart, we can be able to notice that the yellow dotted one, which shows the perovskite based device and their solar cells. So it is started to report in the year of 2013. With a short span of time, it has been reached almost 24.2% efficiency. So this is the very spectacular improvement on this particular perovskite based devices. This shows a huge attention on among the world researchers, those who are working in the field of DSSC, thin film solar cells, and silicon solar cells also, they have switched over to these new modern perovskite devices because of these superior properties than other materials. So this is the progress of the perovskite solar cells. So in the 2005 and 9, they have reported the first perovskite solar cell with an efficiency of 3.8 efficiency. And after that, people have started to work on this material, and they have almost reached 24.2 percentage. And each and every era, people have started to look on different aspects, addressing the issues of hysteresis, interfacial engineering, and material selection for the high efficiency, because the high efficiency is an expected one for these solar cell materials. And people also looking on compositional engineering on these perovskites and their improvement in both efficiency and stability of these materials. And nowadays people have started to work on long-term stability, which is considered as a major concern for these perovskite solar cell devices, and as well as the issues of moisture, thermal, and photo instability. So that's those two are the most drawback of these perovskite devices. If we optimize those parameters, we can be able to get some good fruitful result from these perovskite devices. So perovskite crystal is mainly classified into two categories. First one is called organic, inorganic halide perovskite, and the second one is called inorganic oxide-based perovskites. So inorganic oxide-based perovskite system are classified into two categories. One is called doped perovskite, and another one is called intrinsic perovskite. So we are not going to discuss that. We will be discussing about halide-based perovskite system, which are all available in the 0-dimensional to 3-dimensional structures. So the diversity of these perovskite systems can be able to adapt to synthesis by different methods, like different forms, including precipitation, hot injection, salvothermal, sonochemical, microwave, and anything. So with the help of those methodologies, we can able to prepare spheres, cubes, rods, wires, platelets, wires, rods, and etc. As I mentioned earlier, the perovskite crystal structure, which is having the stoichiometric ratio of AMX3 plus 1 A side cation plus 2 B side cation, and X must be a halide atom. And these perovskite materials are having excellent properties like high tunable band gap, high absorption coefficient, broad absorption spectrum, high charge carrier mobility, and log charge diffusion lanes. So these are the 5 major properties of this perovskite material to use them for a multiple optoelectronic devices application. So this is the person who is Lev Perovsky. The perovskite system was named on behalf of his inventions and his contributions to the development of these material systems. So as I mentioned earlier, various number of A site, B site, and halide atoms have used so far in the perovskite community. So we will be dealing about halide based system, different combination of the ABX3, AB A2B6, A3B29, A2B6, different various composition of the halide perovskites are also available. So based on the valence atoms, various +1, 2 plus, 3 plus B side cations and halide atoms have been changed and replaced with the traditional halide system, halide perovskite systems, which is expected to useful for the future low-cost perovskite fabrication applications. So in order to consider to fabricate or to design any perovskite material, one factor is much essentially to be considered. That factor is called a tolerance factor. The tolerance factor, which relies on the ionic radius of A site, ionic radius of A atom, B atom, and the X halide atom. So if the tolerance factor is approximately equal to 1, then only it will be an ideal perovskite material. If it is greater than 1 and less than 1, it will lead to form some kind of other structures that will not be useful, but they also sometimes useful for the other purpose applications. So in this table, people have listed out various number of tolerant factor and their optical band gap value, which they have identified on the particular materials, including cesium lead chloride, methylene, lead iodide, and the tolerant factor and band gap value. So are listed out here. Some materials are not able to produce the band gap value due to the high tolerant factor. So that must be a considered one. The tolerant factor must be approximately equal to 1. Then only that perovskite will be useful for the PV application. Not only PV, other photovoltaic and optoelectronic device applications also. So the application of a perovskite is on various fields, from the photodetectors, field emitting transistors, solar cells, photoluminescence, visible light communications, X-ray scintillators, lasers, and light emitting diodes. So these are the most prominent area of application of this perovskite in modern optoelectronic devices. So as I mentioned earlier, this perovskite is not a new one. It has identified in the year 1893. So at the time they have just fabricated this material and they have just reported that these are some kind of a formation that can be easily formed. ABXC like that structure can be fabricated, and after that in 1958 people have started to identify and study their photoconductive property, and after that in 2009 Tom Yasaka group has first adapted this synthesis of perovskite materials and their film fabrication for the application of solar cells. So this is the first report published by the Tom Yasaka group, and it is mentioned here that they have achieved only 3-point power conversion efficiency only. At the time, it is identified that the important one because they are having good properties, good excellent properties, especially for the optoelectronic device applications. They have proper bandgap value around 1.55 electron volt, and they have high absorption coefficients, low exciton binding values, high dielectric constant values, and transport charge carrier transports, and it is immunity to the intrinsic defect, and it is long carrier lifetime, which is considered as important property for the application of optoelectronic devices. So when we compare with the other already available solar cell materials to the perovskite based systems, so this is the comparison made between the cadmium telluride, copper indium gallium sulfide, and the crystalline silicon based material systems. So the raw material cost is very much low, and finished material cost is also very much low compared than the other materials. The important one is the efficiency is very much high than the other materials. So this is the most important aspect to look on these perovskite based systems for the application of future electronic devices. So this is how a perovskite solar cell is working. In simple, if a sunlight falls onto the perovskite material, the perovskite material will separate the charge and charges like holes and electrons, and the electrons will transfer to the transparently conducting electrode region, and the holes will come to the counter electrode region that will go to the circuit, and it will receive it from the circuit also. So this is the kind of a short schematic diagram of the simple perovskite solar cells. On the transparent conductive oxide glass, coated glass, we have to deposit whole transporting layer. The whole transporting layer may be titanium dioxide, zirconium oxide, and zinc oxide based systems. And the perovskite active layer must be fabricated and must be deposited with the help of spin coating. Nowadays, people have deposited this perovskite by using different methodologies. And the electron transporting layer, people have used many polymeric based material like PE.PSS, pyrometad, B3HT. Many polymeric material have used them. And the conductive contact, for the conductive contact purpose, people have used silver, gold, and nickel and contact for the PSA applications. As mentioned earlier, that these are the various architecture of the perovskite solar cells. So mesoporous based titanium dioxide, which is called mesoporous based titanium dioxide, used as a electron transporting layer, and planar Ni PN junction structure, and inverted PN junction structure, and whole transporting material free structure also. So in this structure, some kind of a zirconium oxide based material and mesoporous titanium dioxide based material will act like a N-type and P-type structures from that they can fabricate the solar cells and devices, and they have also exhibited some kind of a reasonable power conversion efficiency. So in the bottom of this slide, I have given the various number of materials, various number of perovskites used for the for the application of perovskite solar cells. So in traditional, the transparent electrode must be made up of by indium tin oxide and fluorinated tin oxide based systems. And as I mentioned, that electron transporting layer may be tin oxide, zinc oxide, and titanium dioxide based material. The whole transporting layer may be used by different material like polymeric, inorganic, organometallic, and small molecule material also used for the whole transporting layer applications. So coming back to the metal halide based perovskites, here people have just replaced those methyl ammonium based organic material with the A-side cation with traditional single element material, which are all having +1 cation vacancy. So that perovskite are also available in the different forms in the cubic perovskites, antiperovskites, which are all having different stoichiometric ratio. So the traditional perovskite, cubic perovskite are having ABX3 stoichiometric ratio, the antiperovskite having A3XY, and vacant perovskite having BBF3 and A to B6, A to B6, and A3B6, and various number of ordered and vacancy ordered perovskites are also available. So these are the kind of a theoretical report that these are all the perovskite can be easily formed by adapting some kind of a different strategies that is to be used to fabricate these devices. So this is the literature, which is a interesting literature published by the group of Lepato Manno from the Italy group, Italy. So if you have interested on this perovskite based research, you please look on this work. So they will be giving various number of other perovskites, other metal halide based perovskites, which will be helpful for the better understanding of the future materialistic work. So this Michael Salibak group has published one article based on this perovskite based system in different dimensions like double perovskites, RP perovskite, DG phase, and Arivales phase. So the difference between the each and every phase is like a layer based perovskites only. The number of layers is classified into 1 to 2 to 3, and based on their dimensions, we can be able to fabricate in different structures like quantum dots, rods and wires, crystals, and some kind of other structures like helical structures, tetrabode structure also can be easily fabricated with the help of these multiple phases, RP and DJ phases. So these are my toys. I'm going to discuss on these three materials only, especially on cesium lead chloride, cesium lead bromide, and cesium lead iodide. These are the three toys that I'm going to play with them. So the main important aspect of this metal halide perovskite systems are it is easily able to tuning their properties by adapting the alloying systems, doping the system, doping the various material on it, and vacancy controlation, and nanostructure fabrication, and crystal size enlargement by 0-dimensional to 3-dimensional, and their thickness control between the layers of the particular devices. So by adapting these kind of methodologies, we can able to get some kind of a good properties from the perovskite materials. Also, we can able to fabricate various kind of structure that is called the structural effect of these perovskite systems by like fibers, platelets, and hierarchical structures, crystals, and a very kind of a patterned crystal, single crystal phase also can be able to fabricate it. So when we use this perovskite material to synthesize them, the traditional methodology used to fabricate is called hot injection method. So in the presence of high temperature solvents, we can easily insert some kind of a cesium oleate and lead bromide and other organic acids or organic amines like as a capping agent to fabricate these cesium lead based perovskite systems in the presence of hot injection method. So in this slide, I have mentioned the various number of capping agents and acids and amines like acetate acid, dodecylamine, and oleic acid and octylamine, and the traditional one, oleic acid and oleamine, and oleic acid dodecylamine, and hexanoic acid and octylamine. If we use these two combinations, we can easily get some spherical quantum dots of this cesium perovskites. If we can use this various number of acids and amines, we can easily get rods, platelets, and cubes. If we are using oleic acid and oleamine as a capping agent for preparation this perovskite system, if we control the reaction time period from 5 seconds to 1 hour, we can easily get spherical quantum dots to three-dimensional bulk crystals also we can easily fabricate it. So the traditional methodology is hot injection method. So these are the simple method to fabricate these perovskites. So when we control the ion doping, heterojunction doping, and composition modulation of this perovskite system, that will lead to design a new kind of a perovskite systems. So the design of a perovskite system is a very important one for the current nowadays. So people, those who are working in the field of computational material science, may look at this topic for their research, for their further advanced research also, to change the phase structure instability of this perovskite system, and especially on the defect properties of this perovskite system. So the controlling the defect inside the perovskite is a crucial task. So if we have completed that task, we can easily get a perfect perovskite for the PV applications. And the most important one is the lead, cesium, lead, and cesium other kind of a composition. The lead is a most toxic one. So we must identify an alternative to replace that kind of lead-based material in these perovskite systems. So that must be a kind of a wide different research area in this perovskite area. So as I mentioned earlier, there are different number of divalent, tetravalent, trivalent, and mixed valent states that are used for the fabrication of different structures, especially two-dimensional and three-dimensional layered-based perovskites, metal-deficient perovskites, and dimer perovskites, and double perovskites also. So here I can mention different number of A site, M site, and X site cations. Here I have mentioned only the lead-free based systems only. So instead of lead, people can able to use tin, germanium, and antimony bismuth, antimony, and other kind of materials also can be useful. And some places people have started to use two B site cation, M site cation, that is the plus one, and the 3 plus cation values. For the purpose of 1 plus cation, people have using silver, gold, potassium, indium, thallium based systems. And for the purpose of second M site cation, people using antimony 3 plus and bismuth 3 plus systems also for the preparation of mixed double perovskite structures. So by changing the halide systems, that is halide system of the cesium, lead, chloride, bromide, and iodide, we can easily fabricate, and we can easily deviate the properties of the perovskite system, especially their color luminescent structures. So cesium chloride will be exhibiting blue color into the UV lamp. If we change the chlorine with the bromine, the color will be getting changed to blue color to green color. Again, the bromine getting replaced with the iodine, the color is also getting changed from green to red. So this is the reason of by exchanging the halide atom in this perovskite system, it will lead to give different fruitful colors from the particular systems. So in general, the traditional lead halide perovskite system nanocrystals with the conventional nanocrystal systems, we can easily classify their crystal structure, composition, their structural range and efficiency, photoluminescence, quantum yield, full width half maximum, and their surface ligand, thermal stability, and multi-excited emission, photo bleaching, and the emission rate. So all these properties, all these parameters are identifies as important one for the application of this material, like coastal nanocrystals and ordinary metal chalcogenide and penticide, uh, general core nanocrystals for the application of devices. So compared than the traditional conventional nanocrystals, the perovskite materials are producing high and reduced and moderate based levels for the satisfaction of the properties which is needed for the fabrication of devices, especially on electronic devices. So for the preparation of these perovskite systems, people are using two different methodologies. One is called injection, and another one is called non-injection based systems. In the injection based system, people are using anti-solvent assisted method to hot injection methods. So in that two kind of injection based systems, we can get some kind of a fruitful and particular size constrained materials from the this kind of two methods, like a good size and morphology control. And these two methods are important for the and suitable for the doping and alloying. If you want to doping lead with the tin and germanium, antimony, bismuth, we can easily dope with them, and we can also play with their structure also. In the non-injection method, it is including traditional convection methods, solvothermal, microhydrothermal, microwave, and ultrasonication processes to fabricate many advanced perovskite systems also. So among those listed out 7 structures, I will be discussing about some of the few preparation techniques for the perovskite systems. So these are the 4 methodologies that I have been adapted to fabricate the perovskite nanomaterials. First one, I have used hot injection methods, and second one is called a LAP method, ligand assisted reprecipitation methods, and third one is called ultrasonication method, and fourth one is called hydrothermal method, and fifth one is called microwave synthesis methodology. So after prepared those perovskite nanomaterials, the film was fabricated, especially the thin film was fabricated by adopting these methods. There are various list of thin film fabrication methodologies available: chemical bath, spin coating, dip coating, daughter blade, and screen printing, inkjet printing. So here I have used some very simple technique like spin coating and dip coating method only, and some research I have used daughter blade and spray coating method to fabricate a perovskite based thin films. So this is our first work. We have just used methylammonium lead bromide based perovskite material. By preparing the simple mortar and grinding methodologies only, we have adapted to prepare this methylammonium lead bromide and methylammonium lead iodide based perovskites only. And those two materials are dissolved in the DMF and gamma butylactone solvent. That solvent used to fabricate this kind of devices in the titanium dioxide, mesoporous titanium dioxide coated films. So these are the SEM image of the TiO2 and methylammonium lead bromide based perovskite film, and this is the device. Solar cell was fabricated with the help of those devices also. And this is the first power conversion efficiency results when we use traditional titanium dioxide based perovskite without titanium based mesoporous material. It is exhibiting 8.98% power conversion efficiency. And if we include some kind of material like titanium dioxide, mesoporous titanium dioxide onto that, it will easily exhibit and it will easily increase the power conversion efficiency from 8 to 11.32 power conversion efficiency. So this is the initial research work that we have made on this particular research on perovskite systems. And this is our second work that we have used hot injection synthesis methodology to prepare cesium lead halide perovskite systems. So under the inert atmosphere, we have used lead halide systems, oleic acid, oleamine, and octodouble decalamine solvents in the presence of nitrogen atmosphere. And we have prepared these 3 systems: cesium lead chloride, bromide, and iodide systems. And the characterization for the cesium lead bromide system are shown in this here, and they come kind of a nano brick structures. Is some kind of a structure has been identified from the cesium lead bromide system, or also we have employed and we have played with the cesium lead bromide with the different structures like ABX3 to A4B6, like that is a new kind of cesium lead halide perovskite system. So that also we have prepared with the help of hot injection based synthesis. So this is the TEM analysis of the cesium lead bromide system. It is a very fine single nanocrystals are easily identified from the help of a TEM analysis, and the average size of the prepared materials lies in the range of 10.8 nanometer only. Very fine tuned, controlled nano.
Sir? Excuse me, sir. You are not audible. Sir, kindly unmute your audio, sir.
Yes.
Okay,
Yeah,
sir.
is
Thank
that?
you.
Yeah, there was some internet disconnectivity has been. Now it is fine.
Yes, sir. Fine. Yes, sir.
Yeah. Yeah, so these are the different CCM-led bromide-based system that we have prepared with the help of a heart injection methodologies. We have achieved some fine size-controlled structures in the range of 12 nanometer to 15 nanometer, 27 nanometer, and 37 nanometer. So some kind of nano heterostructures like very small nano rise, nano pentagon shape structure also is observed from the STEM images. And after that, we have fabricated these perovskite solar cells by adapting these simple spin coating methodologies. So we have taken some fluorinated tin oxide substrate and we have deposited mesoporous tin oxide materials with the help of a simple spin coating method. And above that electron transporting layer, we have deposited some kind of a perovskite materials, perovskite solution, especially cesium-related bromide solutions with the help of simple spin coating method. And above that perovskite layer, we have coated pyrometered layer, that is like a whole transporting layer again with the help of spin coating method. And after that, we have deposited gold as a contact layer for the perovskite system with the help of electron beam evaporation method. So this is the typical cross-sectional image of the prepared perovskite system. So FTO, TiO2 perovskite and spirometered layers, and above that contact layer also easily visible in this cross-sectional image. So I'm very happy to introduce the first result of this cesium-related bromide-based perovskite system. We have achieved almost 11.9% efficiency in the cesium-related bromide-based systems. And as I mentioned earlier, that the lead-free perovskite research is attracting nowadays, especially because of the high toxicity of the lead. It is in the material. So lead-free perovskite will be produce some kind of a fruitful applications, fruitful area like a high cubic symmetry of this perovskite material, lone pair cations, and stronger bonding between the other materials also. So that's why this lead-free perovskite research work also we have done. So for that, we have adapted different combinations from the APBX3. We have changed that lead with different cations, maybe chalcogenides and rare earth materials and other actinide materials also, or lanthanum materials also we have used, and some transition metals also replaced with the lead. So with that structure, APBX3, A2B4, A3BX9, A3B6, and A2B6, various number of lead-free perovskites by replaced by isovalent and heterovalent element materials on the structure. So these are some kind of advantages, disadvantages of this lead-free perovskites. So if we use some isovalent materials and heterovalent material, the main prime objective of this lead-free perovskite is it must be a stable one in the room temperature, and it should not affect by any deep effects, and it must be produced some kind of a good suitable band gap devices, band gap properties, so that will leads to apply for this material in different electronic device applications also. So for that, we have prepared cesium tin iodide A2B6 structure. We have just replaced lead with the tin, and we have achieved almost 5.51% efficiency from these particular devices. So we have prepared cesium tin iodide with the help of hydrothermal method. with the help of oleic assisted hydrothermal method, and the some images are also showing some kind of a fine-tuned particles are available. We are working on this material for the fabrication of other prospect like tin and LED and other food detector applications also. So far I have discussed about the perovskite application of the perovskite in solar cell field. Hereafter, I would like to give kind of a brief introduction about the application of perovskite in other optoelectronic devices like light emitting diodes, lasers, photoluminescent plates, and detector also. First of all, I would like to discuss on LED-based systems. So the main difference between the high pressure sodium vapor lamp and LED is that's kind of a clear-cut images, and their clarity must be shown on these LED-based devices only. So compared to the hyper HPS lamps, and LED shows some kind of a clarity one. Okay, so compared to the other material, other lamp like incandescent lamp, HPS, and fluorescent lamps, the insects that not must be getting touched with the LED lamp. It is important that you can also see many various LEDs in the color red, orange, yellow, and ultraviolet, pink, and purple, and violet. So there is no pure white LED which is available on perfect pure LED. So there is no perfect pure white LED is not available. In some, white LEDs are available with the help of you can easily make some blue, some kind of yellow pass per mixed composite only. So these are the various material used for the fabrication of different color LEDs. People generally use gallium and aluminum and phosphate based systems for the fabrication of LED based LED devices. So this is the simple photo and electrical excitation mechanism which is involved in the light emitting diodes. So if we apply some kind of a electrical potential on this particular material, that perovskite material will release the whole transporting layer, and the electron transporting material will release their holes and electrons. So they will combine each other in the medium of perovskite, and it will come out like a light particle, light emission, which is called light emitting nature. So that's the simple photo excitation property which is involved in the perovskite system to release and to exhibit light emitting nature. So the recombination mechanisms, there are three kind of recombination mechanisms are available. First one is called the trap mediated, bimolecular mediated, and OJ mediated. So trap assisted recombination, which is involving the capture of either electron or as a whole in a particular trap state which is available in the particular device semiconductor material. And this bimolecular combination, which is especially happening in between the holes and electrons. Most of the recombination mechanism happening in the region of OJ recombinations. So this will helpful to combination with the help of a three particle EEH or HEE. So it will transfer the electron from one area, one sector to another kind of sector without changing their holes. That's the important one in this OJ recombinations. So in every light emission process, all these are either one of these recombination mechanism will be involved in the fabrication, in the preparation of light emission in the particular devices. So these are the traditional perovskite based LED materials so far used for the LED applications. So for the electron injection layer and the hole injection layer, people have used many different materials. For the electron injection layer, people are using zinc oxide, magnesium, PE, and titanium dioxide, tetrabutyl ammonium, PCP. And hole injection layer, people use many thiocyanides, copper oxides, and many polymeric based material like P.PSS, P.PSS, and TFE, TPD, and many hole injection layers so far used there. And it is mentioned that there are many few number of literatures are available on cesium based perovskites, especially metal halide based perovskite research work is very limited one. So that makes us initiative to work on this particular perovskite based devices for LED. And we have prepared some kind of a phenyl ammonium with cesium lead bromide based perovskite with the help of a hot injection method, and we have fabricated one LED device and it is exhibiting some kind of light blue color, and it is mentioned that their external quantum efficiency is all about 3.6 percentage. So for this work, we have made a tie-up with the Hong Kong University professor, and we have fabricated this device, and they have tested there itself. And we have prepared some kind of other perovskite based systems with the help of hot injection methods, and we have prepared different color variations, like from you can identify with the CAE diagram and as well as the UV lamp diagram also. So we have used the time variation, the reaction time period variation from 4 minutes to 20 minutes. If we increase the reaction time period, the color is also getting changed from the blue color to green color, it is observed, and as well as the size also getting changed from the very fine nanoparticles to some kind of a large grain size particle size structure also. So that's an important one when we are observe this kind of a perovskite system fabricated in our laboratory with the help of HI synthesis. And we also fabricated some kind of simple ultrasonic cleaner methodology. So we have fabricated cesium-led bromide-based perovskite systems with help of ultrasonic systems in the presence of ethyl acetate and solution. So we have fabricated some small nano sheets, some kind of a small nano rods we have prepared. And that nano rods extend their shapes to nano sheets to fabricate like a nano sheets. So these are all some kind of a platelets coated with the help of these cesium-led bromide solutions on spin coating method. Under the UV lamp, it will glow like a green color. And these are the TEM images of the cesium-led bromide material prepared in the help of ultrasonic cleaner. So they are showing some kind of a very fine sheet-like structures, nano sheet-like structures with the help of this TEM image. And this is the work we have made up a tie-up Taiwan professor to fabricate the devices for the butyl ammonium and cesium-based perovskites. So we have prepared two organic and inorganic perovskite systems. So for the organic cation, we are using butyl ammonium. For the inorganic system, we are using cesium-lead halide systems. So if we couple this metal halide organic and inorganic system, it will easily able to release some kind of emission nature in particular wavelength, like the exact photoluminescence wavelength is depicted here. And the Professor Luncheon group have fabricated LED device and they have tested in their laboratory. We have sent 3 samples. It is exhibiting blue color, green color, and red color emission from that particular materials. These are the, some kind of achievements we have made in this perovskite-based LED devices. As I have mentioned that we have also worked on some quasi two-dimensional organic-based perovskite materials. So we have based phenylethyl ammonium, butyl ammonium, some kind of a different three-dimensional structure perovskite also we have prepared. We have prepared this using simple ligand-assisted reprecipitation methods. And these are their photoluminescence efficiency, photoluminescence intensity with respect to the green color nature, which is expected to identify from this cesium-lead bromide along with the phenylethyl ammonium and butyl ammonium based perovskite systems. And these are their optoelectronic characterization of the voltage versus current density curve, photoluminescence efficiency, and as well as current efficiency with respect to the external quantum efficiency of the perovskite devices, which is made up of by quasi two-dimensional bromide-based cesium-lead bromide systems. So those who are working in the field of perovskite LEDs, there are different variety of opportunities are available. Especially on the perovskite emitting material, there must be different field like anti-solvent engineering, ligand engineering, impurity doping, and compositional optimization methodology and opportunities are available. And especially on device fabrications, these are the 4 kind of prospective areas are available. Modifying perovskite thin insulating layers, balance injection, and exploit the inorganic charge transport layers and thin perovskite layers to increase the stability of the perovskite LEDs. And these 2 other optical defects and advanced encapsulation are also important for the PLED, perovskite light emitting diodes. So So this is the another kind of a third sector that is called a peroptronic device. This is a simple device. In the daytime, it will act like a solar cell. In the nighttime, it will act like a LED. So this is the simple concept of this peroptronic device. So this concept was first introduced in this research published in the AIU report in the year 2014. So this group initially started by Singapore NTU group. They have used a
Excuse me,
material.
sir.
Yes, ma'am.
Sir.
Yes.
Some air sound is coming, sir. It is interrupting your voice. Your voice
Yeah.
seems very low pitch.
Yeah. Oh, 1 second.
Okay, sir.
Yeah. Hope I'm audible clearly.
Yes, sir. It's audible, sir. Thank you.
Yeah. Is that fine? Yeah. Is that fine for you, ma'am?
Fine, sir. It's clearly
Okay, that's
audible
fine.
now.
So
Yes, sir.
yeah. Yeah. Fine. Thank you. Thank you for the suggestions. So in the daytime, the device will act like a solar cells. In the nighttime, the device will act like a light emitting device, like a kind of LED. So that's the concept they have introduced. So this is the simple fabrication process and working mechanism of this peroptronic device. So the peroptronic device can be fabricated by adapting simple solution process, like kind of a simple spin coating method by using spin methodologies, and they have deposited some electron transport layer onto the perovskite substrate, and they have deposited some gold also, kind of a electrode. Okay, so this is the working mechanism of this peroptronic solar cell and peroptronic LED device. So in this peroptronic solar cell device, it will work like a optical energy converted into electrical energy. In the LED device, the electrical energy converted into optical energy. So this is the kind of a initial research work on this particular device. We have also taken this initiative to work on this simple zinc oxide and methylammonium bromide based perovskites. For that, we have prepared some zinc oxide based simple solar cell device, and we have achieved 5.02 power conversion efficiency on this peroptronic device. And with the involvement of some kind of a polymers, electron transporting layers, the power conversion efficiency getting reduced, and it is around 2.41 low power conversion efficiency. And when we check out this peroptronic LED device, LED characteristics, we have received only less amount of external quantum efficiency. But these are all in the initial stage of this peroptronic device that we are working in our laboratory. So for this interesting, I would like to share this peroptronic device results with you all. And other kind of photonic and electronic devices are also available. So compare than the solar cells, LED, and a peroptronic device. Hereafter, I will be giving some kind of a brief overview on perovskites applicable in different electronic devices. So the main purpose of this photonic and electronic devices are to apply this perovskite material for the application of resistor, diode, and transistor applications. So whenever the possible of any semiconductor applied in their structure, they can also use this perovskite material in the replacement of the semiconductor material in the particular tight structures. So that's the concept. So for the application of field effect transistors, many materials are used for the channel, gate dielectric, and transporting layer and photoactive layer. So those layer can be replaced with the perovskite structure. These are all some kind of proposed structures. They are all not yet fabricated, and they are not yet analyzed in detail. These are all in the proposed level. So thus we are working on it with the help of some collaborations around the globe. So the possible fabrication of this perovskite material in the photo field effect transistor and hybrid photo field effect transistor are depicted here. Their schematic structure also stated here. So in general, people are using graphene as a photoactive layer for this hybrid FET applications. So that graphene material, which is called two-dimensional material, can be replaced with a two-dimensional perovskite system also. Two-dimensional layer perovskite also can be useful for the replacement of graphene in this barrister type and photo bipolar junction transistor applications also. So these are the working mechanism of a hybrid perovskite phototransistors. So we can get the current and conductive gain with the help of the charge intercalations between the insulator, drain, and source region. So when we change and when we extract the charge carriers from the particular device, we can be able to adapt these three illumination process: closed under illumination, open channel under illuminations, and some kind of a photoconductive gain also employed in these devices to receive good number of efficiency from the devices. So these are the other kind of photo detectors that are all used for the detection applications. So in general, in our market, people are using cadmium sulfide base, that is a semiconductor based photo detector for the some kind of a project and R&D applications. So that cadmium sulfide semiconductor can be easily replaced with this perovskite detector. The main purpose of changing this CAD CDS is to receive high number of detection capability. So this high number of detection capability will be applicable for the defense and R&D applications, defense applications. So for that, the people are using these photo detectors in two category. One is called two-terminal device, and another one is called three-terminal device. So this two-terminal device, this is called photodiode and photoconductor based devices. And this three-terminal device is called phototransistor. This transistor is mainly used for the electronic applications. This diode and the conductor are used for the defense applications. So here, these devices like a photodiode and a photoconductor are easily fabricated like a vertical type. And this phototransistor can be prepared by like kind of a lateral type. So these all the structures, all the schematic structure can be easily prepared if we have a simple FTO substrate and we have any simple pin coating instrument. So that two instrument is very much enough. Is that enough? More than enough to fabricate this kind of device. The more important parameters that need to be in this research are, if you consider about photodiode, it should be exhibit some kind of high photocurrent. It should not emit low photocurrent, and responsivity, dot current, and detectivity also. So these are the important parameters when compared with the diode, conductor, and the transistor. If we optimize these problems on this detector, this perovskite based photodetector will be a prominent one for the device applications. So these are the traditional detectivity of traditional photodetector based material used for the industrial applications. So main purpose of the detection is to detect multivariant wavelength light. So some material like a silicon and some kind of nanocrystals or organic semiconductor material will detect the light in the range of ultraviolet visible region, and some material will receive detect UV and visible region, and some material like polar quantum dots will detect the light range from near infrared region to mid infrared region. So if a material can able to detect this all region like UV visible and NIR MIR. That material will be useful for the identified as a prominent one for the detection applications, especially for the photo detectors. So for this objective, people have used perovskite material for the fabrication of phototransistor. They are the initial research work that has been taken by Tinkwatz Paza in the year of 2017. They have prepared simple methylammonium lead iodide based perovskite in the perovskite phototransistor fabrications. They have received very low number of efficiency and external quantum efficiency, and it is expected that in another 4 to 5 years this kind of a perovskite transistor will be available. So most of the commonly available transistor nowadays are mainly based on silicon, germanium and gallium based materials only. So it is expected that this material will be replaced by the perovskite with in another features. And this other important prospect of this perovskite based photodiodes. So this photodiode easily exhibit and extract the charge carriers from the perovskite when we apply some kind of external voltage onto this perovskite diode. Okay, so when we apply some kind of potential, it will exhibit some kind of their charge carriers, and the charge carriers will go to the extraction level like anode and cathode level, and from there we can easily get the charge carriers from that. So this is the research. People have started to work on perovskites for the application of photodiodes. And the next device which I'm going to discuss is a laser light amplification stimulate emission of radiation. That's a simple emission process which is exhibited by traditional many other materials. So in that kind of laser, people have using very high cost materials and helium, neon and other kind of neodymium, yttrium, argonium, many other high cost elements are used. So instead of this high cost element, very low cost material also like methylammonium lead halide systems and other material also useful. They are suggested that this material also able to exhibit some light energy. So this material will be useful for the laser applications also. So these are some kind of a rod prepared and they have deposited on a FTO substrate, and under the UV lamp it is exhibiting blue color, green color, red color, luminescence nature. So the evolution of the perovskite laser is started in the year of 2014. So in the earlier, people have identified cesium lead perovskite as a material in the year 1893, and after that, people have started to identify their photoconductivity property in the year of 1958, and after that, the first laser was invented with helium, neon, and other material laser. So the first perovskite based laser was introduced in the year of 2015. Single mode perovskite laser was identified and used, and after that people have using many two-dimensional systems, Robertson Popper and DJ phase based materials, perovskite materials for the laser, especially continuous wave pumped perovskite lasers. So these are the one kind of example of the methylammonium lead iodide based materials which is exhibiting a red color laser light under the influence of some kind of external external field fall onto the particular material under field. So this is the research on methylammonium halide based system which is exhibiting green color laser light emissions. And this is another kind of research work. In addition to the laser, people have started to work on these nanocrystal scintillators. Scintillators, we can see this kind of a scintillator is in airport systems, airport like there. The people they are using X-rays to scan our bag and our belongings to identify any unwanted flammable objects that we are kept in our bag either or not. So for that purpose, people have using many high toxic element like a cesium iodine and cesium thallium based material for the detection applications. So instead of that material, it is proposed that cesium-lead bromide quantum dots are also useful for the application of this scintillation application. So this is the simple kind of a photoconductive mechanism. So when we apply some kind of X-ray material, X-ray light on this material, it will exhibit some kind of a light energy which is in the range of 1.7 to 3.0 electron volt. So these are the high resolution TEM image of the cesium lead bromide, and their emitted photon energy when we apply some kind of external light energy falls onto the particular perovskite material systems. So as I mentioned earlier, this is the conversion mechanism of how an X-ray energy is converted into ordinary light energy with the help of photoconductive mechanism. So the traditional material used here is carbon and cadmium telluride. So this cesium lead bromide is also exhibiting same absorbance level, scintillation intensity level with respect to the already traditional one. So that must be there may be change in the cesium lead bromide with the other traditional material. So these are all other kind of scintillation mechanisms compared than the cesium, thallium, and BGO crystal used for the scintillator applications. So this perovskite exhibiting some kind of a very narrow full width half maxima, which is around 12 nanometer for the scintillation applications. So this is the kind of one kind of a review which is published in the year of 2018 by Osman Bagmud group from KAUST. They have used this perovskite material for the scintillator, and they have used in Apple laptop, and they have identified their inflammable flammable objects in that particular devices, particular object. So we have also taken this initiative, and we have prepared one methylammonium lead bromide perovskite materials in simple some kind of simple mechanical systems, and we have achieved some kind of a current response efficiency from 1.86 10 to the power minus 9 centimeter cube, and the interplanar distance of the methylammonium lead bromide is almost 2.86 angstrom, which is under captured with the help of a Hadaf stem. And the comparison between the traditional silicon, selenium, and cadmium telluride based scintillator material, the prepared methylammonium lead bromide exhibiting excellent absorption coefficient when we fall on some external photon energy onto that particular material. So I will come to the conclusion part. So there are many future challenges are available in this particular perovskite research. If you look over to any day level, seconds level, milliseconds, microseconds, nanoseconds, picoseconds, and femtoseconds, there are variety of opportunities and a variety of struggles are available. If we overcome these properties, that will be good research area for the future PV applications. And especially the light illumination property, humidity, and the electrical bias, and the perovskite composition defect. If there are the many efficiency degradation parameters are available, so if you avoid, if you neglect, if you overcome this overcome this degradation properties, it will leads to get some good number of power conversion efficiency from the perovskite solar cells. Yes, these are the present solar challenges in the PSC: light, heat, and the humidity, which is denotifying the performance of these perovskite solar cells in the industrial level scale. And especially on the metal halide based perovskite system, the heterostructures, dimension tuning, ligand chemistry, and the change in the compositional changing, A site, B site, X site, and the halide deficient, B site doping, controlling the photoluminescence, quantum yield, and oriented attachments are already employed. So people are looking next approach to tune these perovskite systems to reveal excellent properties from them also. So the scope of the perovskite solar cells, these are the 5 area low cost multi-junction to be prepared. It must be very efficient. It is highly efficient in a very small area of device. It must be a scalable one, stable one, and it must show their eco-compatibility to the nature. And when we consider about a good material for the photovoltaic devices, it must be fabricated in a very cheap manufacturing cost, and their material properties should exhibit high optical absorption coefficient, and their stability also must be increased. The most important one, there must be a toxicity problem in the lead. For that, lead-free perovskite can also be considered, and scaling problem also must be avoided. And these are the advances are working on this particular field, materials and devices, especially on deposition and absorber layers, charge collective layers, and transparent contacts. So these are the materialistic aspect. And if you look about some kind of advanced characterization, composition structure, optical, optoelectronic device physics also is an important one. So there are other kind of terms like long-term stability and tandem field is also available. So these are some kind of a collaborative research we are working in the field of perovskite research, film deposition, new material, novel material devices, design, applications, lead-free perovskites, nanocrystals, and quantum dots in different multi-dimensional structures, compositional engineering, and from all these problems we can be able to solve, and we can be able to get some kind of a good power conversion efficiency. So these are the research what we are doing in our laboratory ICANN, Industrial Research Center for Applied Nanoscience. We are preparing this perovskite material, quantum dots, crystals, rods, wires, platelets, and layer type structures, which will help some to reveal the properties like a quantum size effects, higher crystallinity, long-term stability, charge transport, high quantum yield structures. So this will be applicable for the solar cell detector, laser, LED, and memory application also. So we are working on electrical optical properties, structure and synthesis of materials, machine learning and calculations, optoelectronic applications also. So we are also expanding our research work to the large device integrated device arrays and the structured functional devices and the crystal engineering on this perovskite based system for the fabrication of micro and nanopet and halide perovskite systems. So from thin films to monocrystals and monocrystals to large scale device fabrication aspect, we are working on it. So these are the kind of nanopatterning methodologies can be adapted to fabricate perovskite based thin film devices by using top down and bottom up approaches for the fabrication of up to electronic devices. So when we look about perovskite nanocrystal systems, so nowadays people are looking forward to apply this, looking forward to take this material for the commercial viability. In future, we will use novel ligands, compositional engineering, scalable deposition, and some kind of a green solvent that must be an eco-compatible one for the fabrication of these perovskite systems with some good energy efficient materials. So this is the important parameter. We are working on interface loss mechanism and the interfaces between the perovskite layer and the whole transporting layer and the electron injection layer. So that layer, that kind of loss mechanisms that we are working, and it's a very good optoelectronic device field also. So if anybody belongs to physics or engineering background, they may choose this kind of a research topic for their PhD degree or a master's degree also. And we are also it's the kind of a long-term goal. So we will be applying these perovskite based devices for handheld, tabletop, and wearable devices for the wearable technologies. So the four main field. So we are in this first category, optoelectronic materials and device category. So here we have prepared materials, and we have also achieved this optical engineering field also. So these two category we have achieved. We are working on these two, display technology and optical communications. In near future, we will be in another 5 to 10 years, we will be achieving these obstacles in the particular field. So I have discussed about the matter-halide perovskites, their type, structure, properties, and their application of the perovskites in devices, solar cells, LED, laser, photoelectronic devices, and scintillators. And in our ICANN, we are also working in the field of carbon dioxide conversion research with the collaboration from Jeju National University, South Korea, with the help of metal organic framework for the effective catalyst for the conversion of carbon dioxide used into methanol. So I would like to thank the organizing committee members of this faculty development program sponsored by AICTE Training and Learning ATAL Academy, organized by this Department of Chemistry. And I would like to special my thanks to organizing committee members, especially the management members, Sri Krishnaraj Vanavaraya sir, and the patron sir, the secretary, Sri Balasubramanian sir, and especially the chairman sir, Dr. Antony Selvata Daumani, and my special thanks to the FDP coordinator, Dr. Pungudi ma'am, who is the head and assistant professor of the PG Department of Chemistry, NGM College, Polashi, for the opportunity. So I would like to acknowledge my collaborators, friends, and funding sponsors to carry out this kind of research work. So there are a huge number of collaboration I'm handling throughout the globe. So teamwork is a key to handle this kind of interdisciplinary projects. So I'm not working as a alone, as a single. So I am working with the help of these kind of eminent peoples around the world, around the globe. So we are working on the field of same materials with the help of different applications, different device applications. So thank you all for the patience, and I'm always looking for the high quality, good motivated PhD students and active collaborators to work on this interdisciplinary project, especially on the advanced nanomaterials for energy and engineering. So with this, I am concluding my presentation, and I am very happy to answer for your questions.
Thank you, sir. Thank you very much for your wonderful section. Participants can post your questions in the chat box, or directly you can ask questions to the sir. Sir, the
Yes,
questions are posted in the chat box.
I'm not.
What is the
If possible, can
solubility
you
of
read
this
out it, ma'am?
material?
The solubility of a material, we are using gamma butyroactone and DMF to dissolve this material to prepare the solution for the.
Are these materials were fabricated using spin coating or thermal evaporation?
Yeah, for the thin film fabrication, we are using spin coating method only. Thermal evaporation, we are using for the deposition of contacts like gold, nickel, and top contacts. We are using them evaporation method to deposit the contacts.
Okay, sir. Any other questions, dear participants? Kindly share your questions. No questions? Sir, your comment on usage of ionic liquids on queries posted in the chat box. Sir, sir, am I audible?
Yeah, so Swaminathan sir mentioned that any comments on ionic liquids. So ionic liquids also can be useful for the whole transporting layer in the perovskite solar cells. We don't have experience on that, but we have made an collaboration with Dr. Ramesh Gardas from IIT Madras to prepare these ionic liquids for the HTML application in perovskite solar cells. So I am pasting my email ID here in the chat box.
Okay.
If there is any queries or you would like to have a collaboration work or please contact me through this email. Yes, sir.
Hello.
Yes, sir.
Hello.
Sir, you are
Google form on the
Sir, kindly unmute. Sir, is there any query? Jay Ganesh, sir? Any other queries? Thank you, sir. Your talk about perovskite nanomaterial gave us an insight on the emerging applications like phototransistor, photodetectors, electronic device, photodiode, quantum dot lasers, nanocrystalline syndicators, and we have a great learning section. Thank you, sir. Your tips will definitely help the researchers to do useful work and help in the framing their scheme. Thank you very much, sir. Now we have a photo section. So kindly all enable your video. Participants, please enable your video.